Remember that this problem here is a no calculator problem, all right? Now, this isn't our wheelhouse. They give this shape. They say we're going to revolve this about the x-axis there. So we're strong with our integrals. We're strong with our area and volume stuff there. Part A and part C, you see all my work and all my answers there if you just need to check certain parts of this one. But the part A and part C integrals there are pretty darn doable. We just got to be a little bit careful, make sure we're practicing these without the calculator, all right? So for part A, it just says find the area. And we know the area is just top curve minus the bottom curve. So it's going to be that main equation minus 0 for C is equal to 6. So if I plug in the 6 right there, there's my setup for the inside of that integral. And then to get the numbers attached, all right, that's the x's that take you across your shape there. So I got my dx for my integral. So left to right, we're going to go from 0. And then this is also where the graph crosses the x-axis. That's where this equation is equal to 0. So if you set that equal to 0 and you set each piece equal to 0, you'll get the x equals 0. If you take the inside of that square root and set that equal to 0, that's where I'm getting that positive 2. And so that's where we're going to integrate between 0 and 2. So I set up my integral, and then it's just a simple u du. So make sure you set that up. You get points for that. Do your u du. Be careful with your signs there. So you get that x dx to match up, that you balance that -2 with a -1/2. That 6 is already there. So you get a -3. Now, normally, I just leave that as -3 square root of u, and then I integrate it. Then I might switch my x's to u's. I'm just going to do that right there so I don't forget. And then sometimes there's some multiple choice problems where they say, hey, when you convert it to there, and you got u's in the problem, it's a du problem, those numbers attached to your integral change because they're u's right there. So what I did at the very beginning, I took the 2, plugged it in there for the x, got 4 minus 4 to get the 0 for my new top number, my top limit of integration. And I took the 0, plugged it in for the x, got 4 minus 0, which was 4. And so that way, when I got down to the bottom after I integrated, I didn't really feel like plugging the x's back in. If you plug the x's back in, use the original numbers, the 0 and the 2. Or if you want to switch your x's to u's, you could do that right here. You could do that right there. But it's already kind of done for us there. So that's u to the 1/2. When you integrate that, you get u to the 3/2 divided by 3/2, which means you times it by the 2/3. Carry down that -3 right there. You kind of see my work there. And then since I already switched the x's to u's, plug in the top number minus plug in the bottom number. And then without the calculator, remember, do that bottom number first on the fraction. That's 4 to the 1/2. And then so that's really the square root of 4, which is 2. And in your cube it, you're going to get 8 right there. And then you got your negative to get your 16 for that answer there. All right, part B might not be the most obvious thing what you're supposed to do there, but I want you to think simple first, okay, and pick out some key things. They gave us a function in the derivative. So I'm like, okay, they gave me the derivative. I'm most likely going to use this derivative for something. And they said for a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches, right? All right, so I saw this word largest. And to me, that was like, hey, that's like a maximum, right? And we know when we maximize and minimize stuff, that always involves taking the derivative and set that equal to 0. So I said, okay, that's probably what they meant for me to do then. Since I saw largest, that's max, let's take the derivative and set it equal to 0. Since they gave us that derivative, that's probably what they're meaning for us to do. So I took the derivative, set that equal to 0. And then a fraction is equal to 0 where that top is equal to 0. So if I set that top portion equal to 0, you see my work there, you get this x equals plus or minus radical 2, but there is no negative x values on our graph there. Everything's going to be positive. So we're just going to stick with this x equals radical 2. Now, and then they give us the original function, right? So if I know my max radius is going to occur at that x equals radical 2, and if you think about it like this, when you take this thing and you spin it around the x-axis right there, right? Like when you do this distance right here and then you spin it around, it's going to create this whole three-dimensional shape. That is the radius of that thing right there. And then they tell us, so that's like the y. The y is like the radius of that shape, and then we're going to spin it around and it's going to create some three-dimensional shape around that axis right there. So, and then they give us the curve right there. So, all right, so we're just trying to use this thing somehow. So once I found my x was square root of 2, I then took that square root of 2, plugged it into the original function, right, for the x. So I had the square root of 2 there, had the c, and then 4 minus radical 2 squared, that's just going to be 4 minus 2. So I just plugged that into the original function, and that was able to give me y is equal to 2 times c. And then since they told us that that thing was 1.2, I plugged that 1.2 in place for the y, and then I got 2c is equal to that. So I divided both sides by 2. So 1.2 divided by 2 gave me that 0.6 right there. So I thought that might have been a little bit tricky for the part B, but Hopefully makes a little bit more sense right there. But again, you see a derivative, you see largest, think maximum, take the derivative, set it equal to 0, and then start plugging some stuff in. And it's not meant to be some crazy thing for us to do there. So you had to figure out what that C value was, and you got to use that 1.2 somehow. All right, so again, when you revolve that, it's, you know, it's creating a three-dimensional shape, and that's kind of like half of it for the radius. So know to take that 1.2 and plug that in place for the Y right there. All right, for the last part of this, I really like this problem because we know how to do it. When it says the volume, you got to think, okay, if I spin this thing around there, my equations in terms of x's, I can do capital R and little r there. I can do a basic disk method on this problem right there. It's a really basic disk method. You guys are all solid with your volume stuff and with this disk method. So they told us the volume was 2 pi. So I said my capital R was the distance from that axis of revolution up to the curve. So I drew my rectangle perpendicular to that axis of revolution. And when I do from the x-axis up, that's always y, which is my main equation. And the little r is the distance from your axis of revolution to your closer edge, which is the same, which is equal to 0. So I'm going to set this up. It says volume. So I know I'm doing volume. So I did pi times my capital R squared minus the little r squared. So I did my capital R squared. This is all multiplication. So I was just able to square each piece right here. So I squared that, made the radical disappear. That's my capital R squared minus my little r squared. So this, and then you're going again from 0 to 2, like we talked about at the beginning there. So remember that pi guy out in front? And now that's the integral expression to find the area, to find the volume of this spinning toy that we're making. But then they told us that volume is equal to 2 pi. So then I got my expression for the volume, set it equal to the 2 pi, and then the c squared was a constant. So I pulled that out along with the pi, took the x squared and just distributed that. They give us a pretty straightforward integral. It's just your easy power rule. So you got that for your integral. Integrate it real quick, plug in the 2, minus plug in the 0. I know 2 cubed was 8 times 4 is 32, 2 to the 5th was 32, and I use 15 as a common denominator right there. If you need to go to the side and be really careful, you can go to the side and actually physically write out like 32 times 5 to get the 160, or 32 times a 3 to get the 96. Like go to the side and write down your basic arithmetic if you need to right there. And I knew 160 minus 100, remember no calculator on this problem, 160 minus 100 would have been 60, but you're only subtracting 96 there. So that's going to be 64 over 15. And then remember to carry down your pi c squared, set that equal to the 2 pi. So if you divide both sides by pi, the pi's are going to cancel. I multiplied both sides by the 15 over 64, which became that 30 over 64. I reduced that. And then you're supposed to square root both sides. You don't need to, I could play around with this and I could rationalize that if I wanted to and kind of simplify that a little bit more, but you don't need to. You can leave left it as a 30 over 64 if you wanted to right there. You don't necessarily need to simplify those larger fractions if they are giving you larger fractions right there, but just square root both sides and then you find that value of C. So I like that problem, but be really careful without the calculator. We could be perfect with these types of integrals right there. And then that one might have been a little bit tricky. You might not sure what to do, but that's why we're practicing these so we just get better with these. Ladders.